Welcome to your very last AP Statistics video on Chapter 27, Inferences for Regression. This is Mrs. Brown, and I am once again here with Daisy and Scout, and we are ready to talk about inference for regression. Our chapter example revolves around the relationship between percent body fat and waist size in inches. Here is a scatter plot of our data set. In regression, we want to model the relationship between two quantitative variables, one the predictor and the other the response. To do that, we imagine an idealized regression line, which assumes that the means of the distributions of the response variable fall along the line, even though individual values are scattered around it. Now we'd like to know what the regression model can tell us beyond the individuals in the study. We want to make confidence intervals and test hypotheses about the slope and intercept of the regression line. We know better than to think that even if we knew every population value, the data would line up perfectly on a straight line. In our example, there's a whole distribution of percent body fat for men with a 38-inch waist. You can see that here. This is true at each waist size. We could depict the distribution of percent body fat at different waist sizes like this. So here you have the different waist sizes, and then here's all the different responses and the number of responses at the different percentage body fats. This model assumes that the means of the distributions of percent body fat for each waist size falls along the line, even though the individuals are scattered around it. The model is not a perfect description of how the variables are associated, but it may be useful. If we had all the values of the population, we could fit the slope and intercept of the idealized regression line explicitly by using least squares. We write the idealized line with the Greek letters and consider the coefficients to be parameters. Beta 0, or beta sub 0, or beta naught is the intercept, and beta 1 is the slope. Corresponding to our fitted line of y hat equals b0 plus b1x, or however you want to express that, a plus bx, if you want to do y equals mx plus b, as long as you put hats on the y's, you're all good. So for the ideal line, though, we do the mu of y is equal to beta 0 plus beta 1 times x. Now, not all of the individual y's are at the means. Some lie above the line and some below. Like all models, there are errors. Denote the errors by epsilon. These errors are random, of course, and can be positive or negative. When we add error to the model, we can talk about the y's instead of the means, okay, because that takes us back to the original values. This equation is now true for each data point since there is an epsilon to soak up the deviation and gives us a value of y for each x. All right, so assumptions and conditions. Well, first of all, we have to be talking about a linear association. So, of course, we have to have quantitative data. And then when we look at the scatter plot, it needs to be straight enough. If the scatter plot is straight enough, we can go on to some assumptions about the errors. If not, stop here and consider re-expressing the data like we did in Chapter 10 to make this scatter plot more nearly linear. Number 2, the independence assumption, and we usually do that with randomization. We want to make sure that the individuals are a representative sample of the population, and then we also have to check the residual plot. The residuals should appear to be randomly scattered. Okay, so if you look, we want to make sure they are randomly scattered, and this is just the first thing we look at the residual plot for. All right, number 3 is equal variance assumption. Does the plot thicken? All right, we're looking to see if the spread is thinner in some areas and thicker than the others. We want it to be kind of uniformly spread, and they are. And the normal population assumption, we check the nearly normal condition, and we do that for the residuals. You want to check a histogram of the residuals or normal probability plot or stem plot or dot plot, and make sure if you're using anything but the normal probability plot that you've got unimodal and symmetric. If you're using the normal probability plot, you want to make sure they line up. The outlier condition, you want to check for outliers. If all four assumptions are true, the idealized regression model would look like this. At each value of x, there is a distribution of y values that follow a normal model, and each of these normal models is centered on the line and has the same standard deviation. There is a catch in regression. The best way to check many of the conditions is with the residuals, but we get the residuals only after we compute the regression model. To compute the regression model, however, we should check the conditions. So what are we going to do? So we do the work in this order. First, you make a scatter plot and check the straight enough condition. If the data are straight enough, you're going to fit a regression model and find the residuals E and the predictive values Y hat. Then you're going to make a scatter plot of the residuals, or have your calculator do that and you copy it down, against X or the predictive values. This plot should have no pattern, checking in particular for any bend, any thickening or thinning, and any outliers. If the data are measured over time, plot the residuals against time to check for evidence of patterns that might suggest they are not independent. If the scatter plots look okay, then make a histogram and normal probability plot of the residuals to check the nearly normal condition. You can do either one of those. Or instead of a histogram, you can also do a dot plot or a scatter plot. If all the conditions seems to be satisfied, go ahead with inference. All right. Let's consider spread about the line. Less scatter around the line means the slope will be more consistent from sample to sample. The spread around the line is measured with the residual standard deviation, SE. You can always find SE in the regression output, often just labeled S. Less scatter around the line means the slope will be more consistent from sample to sample. So here we have less scatter. So no matter which sample we have, the slope's not going to vary a lot. Here we have more scatter. So we could end up with samples that have wildly different, vastly different slopes. So we want to check that. We want to know what the scatter is around the line, and we find that from S. Formally, you can say it is the standard deviation of the residuals. You need to be able to interpret SE, and a lot of times people struggle with it, so make sure you pay attention to doing that. All right, the spread of the x's, a large standard deviation of x provides a more stable regression. Having a larger sample size n gives more consistent estimates. Three aspects of the scatter plot affect the standard error of the regression slope: the spread around the line, the spread of the x values, and the sample size n. And we just talked about those. The formula for the standard error, which you'll probably never have to calculate by hand, is given right there. When the conditions are met, the standardized estimated regression slope follows a student's t model with n minus 2, because you've got two variables, degrees of freedom. And so that's going to equal b1 minus beta 1 over the standard error of b1. And the standard error of b1 is that formula you'll probably never actually have to calculate by hand, but it is the standard deviation of the residuals divided by the square root of n minus 1 times the standard deviation of x. And the standard deviation of the residuals is equal to the sum of the squares of y minus y hat divided by n minus 2. What about the intercept? Well, we can write b naught minus beta naught over the standard error of beta naught with t n minus 2 degrees of freedom, but we rarely use this fact for anything. The intercept usually isn't interesting. Most hypothesis tests and confidence intervals for regression are about this slope. Okay. A null hypothesis of a zero slope questions the entire claim of a linear relationship between the two variables. Often we just want to, which is just exactly what we usually want to know. So to test this null, we have beta 1 equals 0, and we find our test statistic by doing b1 minus 0, because that's our hypothesized value for beta 1, divided by the standard error of b1, and continue as we would with any other test. The formula for the constant confidence interval for beta 1 is, just like every confidence interval, estimate plus or minus critical value times standard deviation or standard error. So we've got B1, which is our estimate, plus or minus our critical value of T star with n minus 2 degrees of freedom. And we're going to multiply that by our standard error of B1. As always, the critical value times the standard deviation or standard error is our margin of error. Once we have a useful regression, how can we indulge our natural desire to predict without being irresponsible? Now we have standard errors. We can use those to construct a confidence interval for the prediction, smudging the results in the right way to report our uncertainty honestly. For our percent body fat and waist size example, there are two questions we could ask. Do you want to know the mean percent body fat for all men with a waist size of, say, 38 inches? Or do you want to estimate the percent body fat for a particular man with a 38-inch waist? The predicted percent body fat is the same in both questions, but we can predict the mean percent body fat for all men whose waist size is 38 inches with a lot more precision than we can predict the percent body fat of a particular individual whose waist size happens to be 38 inches. We start with the same prediction in both cases. We are predicting for an individual, one that was not in the original data set. Call his X value XV, which is 38 inches. The regression predicts percent body fat as Y hat V equals B naught plus B1 times XV. Both intervals take the form Y hat of V plus or minus the critical value of T with n minus 2 degrees of freedom times the standard error. The difference is in the calculating of the standard error. So if you look, here we have our standard error for the mean response, okay? And if you look, it's going to match up exactly with our standard error for the individual response, but the individual response has one extra term of the standard deviation of the errors or of the residuals squared. So we add an extra variance of the residuals underneath the square root sign, and that adjusts the margin of error in just the right way to account for the increased variability among individual responses. Keep in mind that the distinction between the two kinds of confidence intervals, the narrower interval is a confidence interval for the predicted mean value at X, our particular X value. The wider interval is a prediction interval for an individual with that X value. Here's a look at the difference between predicting for a mean and predicting for an individual. The solid green lines near the regression line show the 95% confidence interval for the mean predicted value. The dashed red lines show the prediction interval for individuals. So you can see there's a great deal more error whenever you predict for individuals. Okay, let's look at an example. One way to measure job satisfaction is to see how frequently people quit their jobs. The following printout analyzes how often people quit their jobs at a particular company based on different salaries with n equals 15. It compares hourly wages to quit rates, and that's defined quits per 100 employees. So we want to know what the explanatory variable is, the response variable, the correlation, remember that's R, and the p-value for the significance test of slope. All right, so when you look over here, there's going to be something that says predictor or variable, and you'll have something that indicates a constant. So the coefficient for that would be the y-intercept. And then you have another variable that is somewhat defined there, so average wage. And the coefficient for that is the slope. Also, in this particular set of output, they give you the actual least squares regression line. So we've got predicted quit rate equals 4.86 minus 0.347 average wage. So average wage is what we is our input, and so that is our explanatory variable or predictor variable. Our response variable is quit rate. The correlation, let's see, they give us R, and so we look to the slope, they give us R squared. So we're going to have to square root it, and to determine whether we want the positive square root or the negative square root, we consider the sign of the slope, because the sign of R is going to be the same as the sign of the slope. So since we have a negative slope, we're going to have a negative value for our correlation. And when you do the square root of 0.729 and apply a negative to it, you're going to get negative 0.854. All right, so our p-value for the significance test of the slope, which is that the null, that beta 1 is 0, the alternative hypothesis is beta 1 is not equal to 0. And if you look, what you're looking at to get that, see how for both predictors here, we have a t ratio. And then we have the p. That's the p-value. So we look at the one for average wage, and we get 0.000. Do the data present sufficient evidence to conclude that our average hourly wage rates contributes useful information for the prediction of quit rates? And then what does the model suggest about the relationship between quit rates and wages? Yes, due to our low p-value of 0.000, and the relationship is moderately strong, negative, and linear, and we get that from our correlation coefficient. What is the predicted quit rate for a job that pays $8 per hour? All right, so X is the average wage, Y is the quit rate, so Y hat is going to be 4.86 minus 0.347 times 8, and we get Y hat equals 2.084. Construct a 95% confidence interval for the slope of the line, and we want to interpret it. So we take our estimate for the slope. I went ahead and rounded to 3 decimal places, so negative 0.347 plus or minus the critical value of t with 13 degrees of freedom times our standard error, which we can get right here where it says standard deviation. You just look at the correct row. Since we're working with our independent variable, our explanatory variable, we're going to use the 0.58 rounded to 7 standard error. And so we get our margin of error, we add and subtract it from our prediction, and we get negative 0.474 and negative 0.220. So based on this data, we are 95% confident that on average there is about a 0.22 to 0.47 decrease in quit rate for every additional dollar in average hourly wage. A 95% prediction interval for the quit rate in an industry with an average hourly wage of $9 is given at the bottom of the printout. Interpret the result. We are 95% confident based on this data that on average, an individual quit rate would be between 0.656 and 2.829 for $9 per hour. All right, let's do the same thing for the confidence interval. We are 95% confident based on this data that on average, the average of all quit rates, or the true average quit rate, will be between 1.467 and 2.018 for $9 per hour. Suppose that the slope for the entire industry is negative zero point 0.6. Conduct a test to see if the true slope for this particular company is negative zero point 0.6. So for this hypothesis test, our hypothesized slope is negative zero point 0.6. So our null is beta 1 equals negative zero point 0.6. And then we use the two-sided alternative. We get a test statistic of 4.32 with 13 degrees of freedom. And so our p-value is going to be 0.0008. Due to our small p-value of 0.0008, we reject the null. There is significant evidence that the true slope is not negative zero point 0.6 for quit rate and hourly wage. Notice that we use the TCDF, the cumulative distribution function for t-values, and our CAS to find our p-value. Suppose that the y-intercept of the entire industry is 0. Based on the computer output, what would be the correct conclusion for a test of true y-intercept equals 0 versus true y-intercept is not equal to 0? Well, we look on the constant row and we look at the p-value, and so that would be 0.00. Based on our small p-value of 0, there is significant evidence to reject the null. There is significant evidence that the true y-intercept is something other than 0 for the quit rate and hourly wage. Okay, so looking at G and H, one thing I want to point out is as long as your null hypothesis is that the appropriate parameter is equal to 0, so with the y-intercept, as long as our null is that the true y-intercept is equal to 0, the p-value provided is one we can use. As long as our null hypothesis when we're considering slope is that beta 1 equals 0, then we can use this p-value that's provided. But if you look at part G, if we are testing against anything else, we have to go through and do the hypothesis test ourselves. All right, guys, thank you so much for watching this video. Do the problems and try on your own, and we will go over that when we get together. Thank you very much, and I hope you have a great day.